Here's a problem that really tests your data structure instincts: group anagrams. This Pattern Mastery 100 favorite pops up at Google, Meta, and Amazon, challenging you to group together words that are rearrangements of each other. As shown in the image, we're not just checking two words, we're clustering a whole list. If you master this, you'll show interviewers that you can go beyond pairwise logic and handle real-world data grouping. Let's dive in. Here's the challenge. Given an array of strings, group the anagrams together. Anagrams have the same letters in a different order, so eat and tea are anagrams, as are tan and ant. As shown in the image, the output should be a list of lists, with each group containing words that are anagrams of each other. What's tricky? A brute force way would be to check every word against every other, n² comparisons. That's slow. The real trick is to find a unique signature for each group, so you can collect them in n time. The easiest way? Sort each word alphabetically and use that as a hash map key. Every anagram will have the same sorted form. Here's the plan. Create a hash map, dictionary, to group words by their sorted signature. For each word, sort its letters to get the signature key. Add the word to the group in the hash map with this key. At the end, return all the grouped values as a list. We import everything from java.util so we can use handy tools like map, list, hash map, and arrays. These give us the data structures and utilities needed to group anagrams efficiently. This begins our solution class, which contains the full logic for grouping anagrams together. This defines the method group anagrams, which takes an array of strings and returns a list of groups, each group containing words that are anagrams of each other. Before doing any work, we check whether the input is null or empty. If it is, we return an empty list because there's nothing to group. This is a simple but important safety check. We create a hash map called map. The key will be a sorted version of a word. The value will be a list of all original words that match that sorted pattern. Think of it like using the sorted word as a fingerprint. All anagrams share the same fingerprint. We start a loop that processes each string s in the input array. This ensures we evaluate every word exactly once. Time complexity note. We iterate over all n strings on outer cost. We convert the current string into a character array, which allows us to rearrange or sort the letters. We sort the characters alphabetically. For anagrams, sorting always produces the same sequence of letters. Example: eat eat, tea eat, ate eat. This sorted form becomes our grouping key. Time complexity note. Sorting each word takes OK log k, where k is the word length. We convert the sorted character array back into a string called key. This key represents the anagram signature for the current word. This line is elegant and powerful. Compute if absent checks whether the map already has a list for this key. If not, it creates a new empty list. Then it adds the original word s to that list, so all words that sort to the same key collect together automatically. This is like placing items into buckets labeled by their sorted letters. This closes the loop. By now, all words have been sorted into their anagram groups. We return a new list containing all the group lists stored in the map. Each entry in map.values is one anagram group. This gives us exactly the structure the problem wants. This ends the group anagrams method. And this ends the solution class. And that's how this algorithm works. It first creates a unique sorted key signature for each word, then groups all words that share that signature, collecting them into lists. Efficient, simple, and elegant. Let's run our test case with this list of words. We want to group anagrams together, meaning words that contain the same letters in any order should end up in the same group. Our algorithm sorts the letters of each word to create a signature. Words with the same sorted signature get grouped. Eat, tea, and ate all sort to eat same group. Tan and nat both sort to ant same group. Bat sorts to abt stands alone. So the grouped anagram should look like eat, tea, ate, bat, tan, nat, or any order of these groups, because the problem statement allows the output groups to be returned in any order. And our program produces exactly that structure, all anagram groups correctly formed. Even though the expected output lists the groups in a different order, this is perfectly valid since ordering is not required. So, our implementation is correct. The algorithm groups anagrams accurately, and the test case passes just as expected. We begin by importing Java's utility package so we can use helpful tools like list, map, hash map, and array list. This defines the class solution, which holds our grouping anagrams method. This method takes an array of strings and returns groups of anagrams, with each group containing words that are rearrangements of the same characters. This line handles edge cases. If the input is null or empty, we immediately return an empty list since there's nothing to group. Here we create a hash map called map. The key will be a signature, a unique way to represent the letter counts of a string. The value will be a list of all strings matching that signature, i.e., all its anagrams. We start looping over every string in the array. This outer loop runs in O(n) time, where n is the number of words. We create a 26-slot frequency array for the string s. Each index corresponds to a letter A through Z. This gives us a predictable, fixed-size representation of the string's character makeup. Now we loop over each character in S. This inner loop takes OK time, where K is the length of the word. For each character, we increment the corresponding bucket in the count array. This builds a fingerprint describing exactly how many of each letter appears in the string. Closing the character counting loop. We create a string builder to build the signature key for this word. Now we iterate through all 26 letter counts. The goal is to convert this array into a unique string representation. This loop is always O26, effectively O1 because it never grows with input size. We add a hash before each count to avoid ambiguity. Without a delimiter, counts like 1, 11, and 11, 1 might look the same when concatenated. The delimiter ensures every segment is clearly separated. Then we append the actual count number. By the end, the string builder will contain a string like number 1, number 0, number 2, number 0, number 0. This becomes the unique key for all anagrams of this word. Closing the loop that builds the signature, we convert the built string into a final key. This key will be identical for all words that are anagrams of each other. This line is doing something very elegant. If the key does not exist in the map, create a new empty list for it. Then add the current word S to that list. All anagrams naturally group together because they share the same frequency signature. Finish looping over all strings in the input. Finally, we return a new list containing all the lists stored in the map. Each inner list is one group of anagrams. This overall approach runs in O(n)k time, where n is the number of words and k is the average length of each word. Closing the group anagrams method. Closing the entire class. And that's how this algorithm works. It first assigns each string a unique frequency signature, then groups all strings sharing that signature into the same list. Efficient, simple, and elegant. Let's test our function using this input, a single element array containing A. This array represents a list of strings we want to group into anagram clusters, where each group contains words made of the same characters. Here's why the solution works. With only one string, there are no other words to compare, and therefore no possible anagram partners. Our algorithm generates a signature for each word, in this case, just the letter A, and groups words that share the same signature. Since there's only one string, it naturally becomes a group of one. And that's exactly what our program outputs, A. This matches the expected result and shows that even the simplest case is handled correctly. So, our implementation is correct. The algorithm successfully groups the input into its anagram sets, efficient, accurate, and reliable. The big takeaway? When solving problems like this, stop comparing, start categorizing. By identifying unique signatures for patterns, you not only improve efficiency but also show interviewers that you think like a true problem solver. Have you ever noticed how some problems test not just your logic, but your data structure instincts? That's exactly what group anagrams does. One of those interview favorites that shows whether you can move from pairwise logic to true data grouping. We were asked to take a list of words and group together all those that are anagrams, words made up of the same letters, just in different orders. Essentially, it's about finding clusters of rearranged words efficiently. A brute force approach would compare every word against every other, O(n)² time, which is way too slow. Instead, we looked for a smarter way, giving each group a unique signature by sorting the letters inside each word. That becomes our hash map key, and every anagram naturally falls into its matching group. We looped through the list, sorted each word alphabetically, and used that sorted version as the key in a hash map. Each time, we simply added the original word to its corresponding group. By the end, each key represented one group of anagrams. Implement recap. We then ran this logic step by step in LeetCode. No syntax issues, no edge case surprises. The grouping worked perfectly. After running through the test cases, every input matched the expected output, confirming that the hash map method grouped all anagrams correctly and efficiently.